Okay, ladies and gentlemen, can you hear me? Can you see the whiteboard?
Yes.
Okay. So let us begin. Last time we introduced this important combinatorial numbers n choose k. By definition, this number stands for the number of all k element subsets in an underlined or in general in any n element subset. So what do we know? So far, we know the following fact that n choose 0 equals what? Do you remember that? How many empty subsets do we have?
One.
One, exactly one, clearly. What else? N choose n equals?
One.
1. N choose n equals 1. If k is greater than n, how many k element subsets does one have in an n element set?
0.
0. We have some equality, some important identity for these numbers. The one that generates the prominent Pascal's triangle. So n plus 1 choose k plus 1 equals, it equals a sum of two terms. Which ones?
N choose k plus 1 plus n choose k.
Exactly. And our last result considers it gives us a formula. So given k is less or equal than n, then we have an explicit formula with factorials for this number. N choose k equals n factorial over
N minus k factorial.
that is the
Multiply
number
k
of
factorial.
arrangement or injections from k to n divided by k factorial. Okay, that's it. So now let us prove some more facts about these numbers, which are known as binomial coefficients. We shall see why. I say that for every n and k, given k is less or equal than n, then n choose k equals n choose n minus k. How can one prove it? Why is it so? How can one prove it?
Oh, just put the values in the formula that
Into
we
the
already proved.
formula, of course. That's possible, but do we have a combinatorial proof or a double counting proof? Can we count one quantity, one amount in two ways so that we obtain first the left-hand side term, second the right-hand side term? Clearly, by definition, n choose k is just the number of all k element subsets, yeah? But what is n choose n minus k? What is it? It is the number of n minus k subsets. Is it clear? But is it the case that we always have as many k-sized subsets as we have n minus k subsets? Is it the case? Think about that.
Yes.
Why is it so? Assume that we have our set n underlined, and here we have fixed some k element subset. So here we have k elements. Here we have k elements. So why can one obtain such a bijection? Where can one map this X to obtain an n minus k element set? We need a bijection between k-sized subsets and n minus k subsets. Do we have one? Please think about that. It is very easy. Ladies and gentlemen, please be more active. Any ideas, please? Is it that hard? Okay. If we take X, what is the complement of X? What is it? How many elements does it have?
N minus 6.
N minus K.
Minus K minus.
This is by which fact? By the rule of sum. So here we have just n minus k elements. So if we map every set to its complement, then we will obtain a function from k element subsets to n minus k element subsets. Is this function injective? Is it injective? This must be obvious for you. If x complement equals y complement, then the complement to the complement equals this number, that is x equals y. So it is injective. Is it clear?
Yes, yes.
Is it surjective? Of course, because every element is a complement of every set is a complement of its complement. So I hope it is clear. So we see that in fact we have as many k element subsets as we have n minus k element subsets. So these two numbers must be equal independently of this explicit formula. Okay, as a corollary of this result, we can easily obtain that for every naturals a and b, a plus b choose a equals a plus b choose b, because b is just a plus b minus a. Is this idea clear?
Yes, it is.
Now, let us see why these numbers n choose k are known as binomial coefficients. Let us consider binomial formulas, say x plus y. Here x and y are just reals. So what is x, xy squared? What is x plus y squared? What is that? You should know that quite well.
Square plus 2x squared plus y squared.
But look, here we have 2 choose 0, that is 1. Here we have 2 choose 1, and here we have 2 choose 2. Probably this is just a coincidence. But what if we take x plus y cubed? What is it? Do you remember the formula? Don't you?
X cubed plus 3x squared y.
xy, really? How
It's
can you?
3x
X
x squared y
y 3
plus 3x y squared plus y cubed.
Of course, it's symmetric. And here we have the same. Here we have 3 choose 0. Here we have 3 choose 1. Here we have 3 choose 2. And here we have 3 choose 3. And in fact, in general, we shall obtain just these coefficients in this binomial formula. Binomial means that we have two terms, x and y, whose sum is raised to some given power. So let us prove the following lemma. For every real number x, for every, it is not that important that x is real. For every natural number n, 1 plus x to the power n always equals 1, that is n choose 0 plus n choose 1, x plus n choose 2x squared, and so on up to n choose n minus 1x to the power n minus 1 plus n choose n x to the power n, or for short, it is the sum of these terms n choose k multiplied by x to the power k, where k ranges from 0 to n. So how many summands do we have here? How many summands do we have here?
N plus 1.
How many?
N plus 1.
N plus 1, exactly. So what do you think? Which method is convenient to prove this theorem? Which method is the most obvious one?
Induction.
Induction, of course, induction by n. So induction on n. Induction on n, by induction on n. So the base case. Assume that n equals 0. So for the base case, we assume that n equals 0. What do we have? 1 plus x to the power 0. What is that? Any number to the power 0 is
1.
1, exactly. And on the other hand, so this is our left-hand side. What about the right-hand side? The right-hand side must equal this sum. And this sum contains how many summands? In general, n plus 1. And in this particular case?
1.
In this particular case, just one summand. So 0 choose 0 multiplied by x to the power 0, which is also 1. So the base case has been proved. Do you agree?
Yes.
This step. For this step, we may assume some inductive hypothesis. In this case, the inductive hypothesis is as follows: 1 plus x to the power n equals our sum from 0 to n of these terms. And what is required? What is required? We need to prove that 1 plus x to the power n plus 1 equals what? It equals a sum where k
From 0 to n plus 1.
runs from 0 to n plus 1, and we have what? N plus 1 choose k, right?
Yes.
multiplied by x to the power k. Okay, let us prove it. So let us denote this as LHS, the left-hand side, and this as RHS, the right-hand side. So first, let us start with this left-hand side. It is 1 plus x to the power n plus 1. That is 1 plus x multiplied by 1 plus x to the power n. And here we have the only place in this proof where we are going to apply our inductive hypothesis. So we obtain 1 plus x multiplied by this sum. This is by the inductive hypothesis. Do you agree?
Yes.
But here we obtain one copy of this sum plus the same sum where the degree of x has been increased by 1. What should we do with that? What should we do with that? It is, of course, it is important to consider like terms and group them together. Is this idea clear?
Yes.
Yes.
But here we have x to the power k, and here we have x to the power k plus 1. How can we make them like? So one way to do so is to rename. One way to do so is to rename k to, here let us rename k to k minus 1. That is, let us now call k plus 1. Let us call it k. So if k ranges from 0 to n, then k plus 1 ranges where from where to? If k runs from 0 to n, then k plus 1 runs from Is this idea generally clear of this renaming? You can rename it to say m if it is not that clear, that you can rename it back to k. So if k ranges from 0 to n, then m, which is k plus 1, runs where from where to?
0 to n plus 1.
0, really? K is from 0 to n, then k plus 1 is?
From 1.
From 1 to n plus 1, exactly. So here we shall have not k, of course, but m minus 1. Here we shall have m minus 1, and here we will obtain x to the power m. Is this idea clear?
Yes.
Okay. But now we can rename, of course, an experienced mathematician does not need this step. We can rename m back to k. So we shall have the following sum. N choose k multiplied by x to the power k plus another sum. But here we have k ranging from 1 to n plus 1, n choose k minus 1, x to the power k. So here we have like terms. We have like terms, but here we have some other problem. The ranges of k are distinct. So here k ranges from 0 to n, and here it ranges where from where to?
From 1 to n plus 1.
Of course, but do we have any intersection of these two ranges? So here we have from 0 to n, and here we have from 1 to n plus 1. Do we have any meaningful intersection? Where it is?
From 1 to n.
From 1 to n. So, but besides that, we have two side terms, I say. So when k equals 0 in the left hand side term, so we have n choose 0 multiplied by x to the power 0 plus this sum. Now it ranges from 1 to n, n choose k x to the power k, and here we have from k to n k minus 1 multiplied by x to the power k plus one more term when k equals n plus 1. So that is n, choose n multiplied by x to the power n plus 1. Do you agree?
Yes.
Okay. But look, what do we have here? So here we have what we have, and in these two middle terms we can group like terms together. So we have n choose k plus n choose k minus 1 multiplied by x to the power k, and here we have these things. What is our next step?
You use the Pascal identity to rewrite
Exactly. Here we have n choose k plus n choose k minus 1. This is similar to the right hand side of this identity. So we will obtain n plus 1 choose k. We will obtain n plus 1 choose k. So by Pascal's identity, this is just n plus 1 choose k. But what about these terms? Look, finally, we are interested in here we're interested in terms of the form n plus 1 choose k. And indeed, here in this middle part, we have obtained just this term. But what should we do here? Can we replace it by something of the form n plus 1 choose something?
Just by n plus 1 choose 0, it will be 1.
Of course, this is 1, and it still be 1. It will still be 1 if we replace n plus 1, if we replace n with n plus 1. And here exactly we have still 1, and for the same for n plus 1. And now all our summands are of the required form. All the coefficients are of the form n plus 1 choose something, and generally k ranges from 0 to n plus 1. So we get exactly our right hand side, don't we? Any questions? So our step. What is your question? I cannot hear your question.
No questions.
So apparently this is clear. So our induction succeeded. So we have proved this lemma that 1 plus x to the power n equals this sum. And now, as a corollary, we may obtain the general form of our binomial theorem. This is known as the binomial theorem. So for every two reals A and B, whatever, for every natural n, then A plus B to the power n equals the sum of n plus 1 summons of the following form. N choose k multiplied by A to the power k and by B to the power n minus k. And here we need no induction. We can simply apply our previous lemma. But for our previous lemma, A has been fixed to be 1. So we should do something to reduce everything to this situation. So we have two cases. The first case is when B equals 0. Otherwise, we shall just divide everything by B. If B is 0, then A plus B to the power n is what? It is just A to the power n. Do you agree?
Yes, yes.
On the other hand, A to the power k, and here we have B to the power n minus k. And B is 0, it is 0. 0 to some power is 0 always, except just one case. Which one? When does 0 have a non-zero power?
0 to 0.
Of course, 0 to the power 0 is always
1.
it is always 1. It is always 1. So we will have just one non-zero summand, namely that when k equals n. So we will obtain n choose n multiplied by A to the power n multiplied by 0 to the power 0. So it is 1 multiplied by A to the power n. So that's it. Do you agree?
Yes.
Now, assume that B is not 0. Let us take A plus B to the power n. It is the same as B plus A to the power n, of course. And now we can divide everything here by B. So it is B. B is not 0 after all. 1, and here we have A over B to the power n. That is B to the power n multiplied by some binomial. And now it is a good opportunity to apply our previous lemma, which was about binomials of the form 1 plus x, 1 plus x, but here the role of x here is played by A over B. So it will be B to the power n multiplied by n choose k, and here we will have A over B to the power k, where k runs from 0 to n. Do you agree?
Да.
If we move B to the power n into the sum, into this bracket, we will obtain n choose k, and here A to the power k and B to which power? N, of course, minus k, that's it. Quod erat demonstrandum. What is required to be proved. Is this idea clear? A binomial theorem has many interesting applications. One of these is as follows. How can we compute the sum of all binomial coefficients? What is it? What is it? If we take
2 to the
k
power
from, what is it?
2 to the power n.
Why is it? Why is it so? One way to see it is as follows. Which one? One proof is based on our formula. What is 2 to the power n? It is 1 plus 1 to the power n. Do you agree?
Yes.
So according to the binomial theorem, this is just the sum of our binomial coefficients. That's it. But do we have a combinatorial proof, a double counting proof? Can we count one quantity and obtain in one counting this sum and another counting 2 to the power n? What is a combinatorial interpretation of 2 to the power n? It is a number of what? It is a number of what? 2 to the power n is a number of all which objects?
Of all subsets.
Exactly.
Oh.
So we know that 2 to the power n is the total overall number of subsets. Yeah. But every subset of an n element set may have how many elements? How many elements can we have in a subset of an n element set?
At most n. Wait. Could you repeat the question?
From 0, so we may have 0 elements. Is it clear? One
yeah.
element, 2 elements, up to excuse me, we need a union here. Up to what?
Up to n
Up to
underline.
exactly n elements.
Exactly. And sorry.
But clearly, the size of a subset is uniquely determined. It is not possible by the pigeonhole principle that one subset has 2 distinct cardinalities, 2 distinct sizes. So we may apply the rule of sum. We may apply the rule of sum and see that this number, which we know to equal 2 to the power n, equals the sum of these cardinalities, where k ranges from 0 to n. And by definition, each of these cardinalities, the number of subsets of fixed sizes is n choose k. Is it clear?
Yes.
Okay, that's it. This is a combinatorial proof to the same result. And now, let us make a step back and return to one important idea. To this very rule of sum, namely, given A and B are finite, if A and B are finite, then the union is finite, and moreover, we can compute the cardinality of this union. What is it?
The cardinality of A plus cardinality of B minus cardinality of A intersection B.
Exactly. Minus the cardinality of the intersection. Okay. And what do we have 3 finite sets? What do we have 3 finite sets? A, B, and C. What is the cardinality of the union? What do you think?
The sum of each minus the pairwise intersection.
Minus the pairwise cardinalities, the sum of the pairwise cardinalities. plus the cardinality of the intersection of these three sets. Do you remember the proof? By the way, have we proved it?
Yes.
Are you sure?
In the seminar,
What?
in seminar.
Mhm. I haven't got what
في السمينار мы доказали.
no, still no idea. So either we have proved it or not.
Yes, we have already.
We
in the
have.
seminar
Okay. Okay. And basically, this follows from the previous formula. Why? Because A union B union C is nothing else than A union B union C. So we have a union of two sets. And in general, we can continue this line. We can continue this line and obtain an important theorem, which is known as I will omit the proof, but nevertheless, continuing this way, we can obtain an important formula, which is known as inclusion-exclusion principle. The inclusion-exclusion principle. And this principle says the following. It is as follows. So assume that we have n finite sets. Assume that we have n finite sets where n is at least one. Then the union of n such sets is finite, of course. This follows easily from our basic result. And moreover, we have an interesting formula for the cardinality of this union. How many elements do we have? Basically, it is the sum, first of all, it is the sum of all cardinalities of our sets. Then, what do we have? All pairwise intersection cardinalities are subtracted. Do you agree?
Yes,
What goes next?
plus the tupled.
Yes, all for each triplet, we add its cardinality. What else? Okay, can you see? Can you hear me? So let us continue. So then we subtract all intersection sizes for all possible tuples of length 4, and so on. And so on. And what will be the last term? What will be the very last term here? It will be -1 to the power n minus 1. And here we have a sum of all intersection sizes where we are intersecting our all n sets. But there is just one way to take an intersection of n sets. Is this idea clear?
Yes.
But how many summons do we have? Look, how many summons do we have here? This is the number of ways to take one set out of n. So it is n choose one summons. Is it clear?
Yes, it is.
How many summons do we have here?
C
N choose 2.
and
Here,
3 and
n choose 3, n choose 4, and here we have how many summons? N choose n, that is 1. Do you agree?
yes.
We can write down this formula in a shorter form. Namely, we can describe every such sum the following way. Let us take all possible intersections of length s, of s sets, and let us require these indices I1, I2, Is to be ordered ascendingly, in an ascending order. Why? Because look, here we take A1 intersected by A2, but not A2 intersected by A1. Is it clear? So we need an unordered pair of our sets. Unordered means there are as many unordered pairs as there are pairs ordered in an increasing and ascending order. Is this idea clear?
Yes.
And here we may take s minus 1, minus 1 to the power s minus 1, where s ranges from 1 to n. That's it. This is a more compact, more concise formula for the same sum. This theorem is known as exclusion principle. Is it clear?
Yes.
And let us apply it to compute surjections between two sets. Let us compute surjections between two sets. As usual, so we're interested in number of surjections. As usual, we shall consider surjections for just for special form sets M underlined, N underlined. So let Sur of A and B be the set of all surjections. So it is the set of all such functions from A to B, where F is surjective for B. Do you remember what does it mean to be surjective?
Yes.
What is it?
For every b that belongs to the
Of
range
course,
of the square variable.
every element from B is the value of our function. And now let us denote by this symbol the number of surjections from M element set to N element set. What will be our approach to compute this number? This is based on the following idea. Let us count non-surjections. So our idea is to count non-surjections, something which is not a surjection. But when something is not a surjection, assume that f is a function from M underlined to N underlined. From M underlined to N underlined. When M is not surjective. When is it not surjective? When it doesn't take some number from N underlined as its value. Do you agree? So there exists such k from N underlined, which is not a value of our function. Do you agree?
Yes, yes.
Or equivalently, that means that either 0 is not a value of our function, or 1 is not a value of our function, and so on up to n minus 1. Yes, so n minus 1 is not a value of our function. Interesting. Interesting, very interesting. So we have n a disjunction of n conditions. Is it possible that neither 0 nor 1 are values of our function? Is such a situation possible? Of course it is. It may take neither 0 nor 1. And let us consider all such functions from M to N, which doesn't take some specific value, some k. So we see that non-surjections, the set of non-surjections is just the union of these sets. A non-surjection is a function that either doesn't take 0, or doesn't take 1, or doesn't take 2, or maybe if some of these values simultaneously. Is this idea clear? Is it clear, ladies and gentlemen?
Yes, it is clear.
Okay, but how many functions which do not take k are possible? So what does it mean that k is not, you know, f still is a function from M underline to N underline, but nevertheless, it doesn't take k. It doesn't take k. It doesn't take k as its value. So what does it mean? This is a function from M to what? To which set?
N underline minus k.
Exactly. So it is a function from m to n, but except k, That's it. And how many such functions do we have? So xk is just the set of all functions, whatever, from m underline to n minus k underline. How many? But how many do we have? We know the sizes of two sets, of two finite sets. How many functions between them do we have? What is it? It is the size of this set to which power? So what is it? What is it? How many functions do we have between two finite sets? Oh no, how many functions do we have in principle between from A to B? How many functions? We proved it. Don't
B
you remember?
cardinality to the A
Size
cardinality.
of B to the power of the size of A. So here we have what? N minus 1 to the
1 to
power
the
M.
power of M.
Exactly. But look, what if F belongs to not one such set, but an intersection of a few such sets? What does it mean? That means that F is a function from M underline to N minus this, all these numbers, I1 and so on, up to IS. So, how many such functions do we have?
X n minus s to the power of m.
Exactly. So it is n minus s to the power m. That's it. So what is the number of non-surjections? It is the number of elements in this union. So our principle, our exclusion principle is applicable. Let us apply the principle. What is the number of non-surjections? The number of non-surjections is the number of elements in this union. So it will be a sum where S ranges from 1 to n, and we have minus 1 to the power s minus 1. It is exactly the same, but look that now our indices range from 0 to n minus 1. But this doesn't matter. They range from 0 to n minus 1. Look. But this number is known to us. This number equals what? We have just computed that. What is it?
N minus s to the power m.
Exactly. Exactly. It is n minus s to the power m. But how many summons do we have here? We have already computed that. How many summons? How many ways do we have to take s distinct numbers from the range from 0 to n minus 1? How many ways do we have to take s distinct subsets, s distinct x's? n chooses summons. Is it clear? And every summand equals n minus s to the power m. So as a result, we obtain this term. Is it clear?
Yes.
This is a number of non-surjections. But how many surjections do we have? It is just the total number of functions minus the number of such functions which are not surjections. Do you agree? It is n to the power m minus our sum. Is it clear? But this term can be described as a term of this form. It is minus 1 to the power 0 multiplied by n choose 0. And here we have n minus 0 to the power m. Do you agree? This minus changes this exponent. So we have a sum from 1 to n minus 1 to the power s. And finally, it is just such a sum where s ranges from 0 to n, and we have minus 1 to the power s, and choose s, n minus s to the power m. This is the number of surjections. Have we had any restrictions, any assumptions on n and m? No, there were no assumptions. So this is true for any arbitrary naturals. Is it clear?
Yes.
But still, we have some corollaries. Let us obtain two corollaries. How many surjections do we have from, say, 3 to 5? How many ways are here to surjectively map 3 elements, put 3 rabbits into 5 cages surjectively? That is, every cage is occupied. How many surjections do we have from 3 elements to 5 elements?
0.
0. It is not possible. It is not possible to make such a surjection. And in general, we know, we proved that if m is less than n, if m is less than n, then the number of surjections from m to n is 0. So as a corollary, we may obtain an interesting purely arithmetical fact. If m is less than n, then this sum, whatever it is, equals 0. You can check it with a computer. This sum is 0. It is necessarily 0. And another corollary is about the case when n equals m. You know, or at least you should know, that if A and B are two finite sets of identical sizes, then if we have two finite sets of identical sizes, then any function from A to B is what? F is injective when?
Whenever it is surjective.
If and only if it is surjective, or equivalently when it is bijective. So between two finite sets of the same size, surjections, injections, and bijections are all the same. Is it clear? So the number of surjections from n to n equals what? On the one hand, according to our formula, it equals this sum. Do you agree?
Yes.
And on the other hand, it equals the number of injections from n to n. And we know this number, the same as the number of bijections. What is it? No, n factorial over what? N minus n factorial. So what is it?
The number of arrangements.
The
Oh,
number of
permutation.
arrangements of length n, the number of permutations. So it is n factorial. Do you agree?
Yes.
We have obtained another non-trivial result. It appears that by a double counting argument, it appears that n factorial always equals this sum. Why? Here we have maybe factorials, but here we have degrees of some numbers, and here we have pluses, minuses, and it appears that overall this sum always equals factorial. Interesting. But on the other hand, this looks like slightly like Taylor's formula. Do you know Taylor's formula from your calculus course?
Yes.
Yes.
It is a little bit similar to that. Okay. So this was an example of combining binomial coefficients and choose k with our inclusion-exclusion principle. And this has allowed us to count surjections and obtain two purely arithmetical facts. One about factorials and another one about this sum, that this sum equals 0 given m is less than n. Any questions?
Nope.
I think that it is enough for combinatorics, and next time we will most likely take some other topic. Thank you.
And thank you.
No, thank you.
Thank you. Goodbye.
Could you please send us the board
The
to the
whiteboard.
please?
Yeah, of
Thank you.
course I will.